right, here we go. This one is number 30. Jocelyn is analyzing the sales of her company. The table below shows the total sales for each of 6 years. So we have our sales in the millions and our years. Of course, the sales depends on the year. So there's a couple ways we can draw this out. We can actually put 2003, 4, so forth. I'm actually going to put years since this is 2000, 2000. Okay, so that way if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and that's plenty of them right there. So years since 2000, and then on my y-axis, I'm actually going to put the sales, and I don't have really space here, so I'm going to put sales in millions. So my sales in millions, I'm going to, since it starts with 30 million, I'm going to go, maybe I want to go up high, probably from 30 to 45. I have a lot of lines. I'm going to say 45 subtract 31, and that's giving me a difference of 14. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. So that's perfect. That's how many lines I need is 14 lines. So I can actually start at 31 and go up. So I would be like 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. It's a little bit above. So that's really kind of close. I could then say, since that is too close, maybe say I'm going to go by 2s instead. So we'll start at 30. And since I'm going to start at 30, I'm going to put a break because I'm actually starting at 30. If I didn't put a break, that means that every unit goes up by 30. But I want to go up by 2. So 30, 32, 34, 36, 38, 40, 42, 44, and 46. So we're going to plot them. 2003, I have 31.2. So 2003 is right here, 31.2. In 2004, it's 34.6. 2004 is 34.6, approximately, oops, right in through here. 2005, 28.9. So 2005 drops down actually to 28.9. So I realized that I've actually labeled my y-axis incorrectly because my lowest value was a 28.9. So I should have started probably about 25. So I can go in now at this point because I say, whoops, I messed up. And we'll go back and do this again. Instead of 45 minus 31, we're going to subtract the 28. Gives me 17. I could probably still go by 2s starting at 28. 28, 30, 32, 34, 36, 38, 40, 42, 44, 46. So we'll do that now. We're going to start with our break at 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and 48. So again, 2003 is 31.2. So don't panic if you mess up with your graph. Don't panic if you mess up there. It's not a huge deal. It's no big deal. 34.6 for 2004. 34.6, so we're up here at 34.6. 28.9 for the 2005. 37.7 for 2006. 37.7. And 41.3 for 2007. And 45.1 for 2008. Now, if I look at that, this is my one outlier. It doesn't quite fit. I could do my line of best fit. There's a number of ways you can do this. We can just say, okay, we're going to try to get through as many points as possible, and that would be our line of best fit. Trying to pass through as many as possible. You can then choose 2 points on that line and create an equation using those. You could also use the stat plot that we did on the last one as well to create the equation. So we have 2 choices here. If I use the actual coordinates, I'm going to use, since it's 2000, the actual values of 3, 4, 5, 6, 7, 8, 9. So this coordinate here was at 4, so it would be 4, 34.6. Second point here is at 7, so it'd be 741.3. And I'm going to create my equation. Don't really have the y-intercept or anything yet, but I'm going to get my slope. So my slope is y2 minus y1 divided by x2 minus x1. So I could say 41.3 minus 34.6. Again, subtracting your y's. If I start here, I gotta start here. 7 minus 4. So let's get that calculator up. Make sure we don't make simple mistakes. 41.3 minus 34.6. And that's gonna be 6.7. 7 minus 4 is 3. So roughly my slope is going to be divided by 3, 2.23. Now if this is my slope, that substitutes in for m in our y equals mx plus b format. So this will go in for m. And I'm going to just choose one of the quarters. I'm just going to choose that last one just because I'm looking straight at it. 41.3 will go in for y. 2.23 goes in for m. And for x, we're going to substitute in the 7. And we're going to solve this for our b value. We need to solve it for our b so that we can get that y-intercept. So coming over here, we're going to do 2.23 times 7 is going to give 15.61. So I'm solving for b. I'm going to subtract that 15.61. And we get 25.69. So roughly, my b value should be 25.69. So they want to make the scatter plot, and if we actually chose an equation, we could write y equals 2.23x plus 25.69. Now, again, we can use stat plot to try to come up with this. I'm going to scoot this one over. And if you want to do that, second plus 712, again, resets that calculator, going into stat, editing our values. Rather than 2,000, I'm going to put 3, 4, 5, 6, 7, 8. Don't use the years. It tends to mess up with the graphs and everything and all the information. And 31.2, 34.6. Double check your numbers as you're putting them in and making sure you have them correct. 28.9. 37.7, 41.3, and 45.1. All right, now we go, again, if you wanted to plot those, you come up, highlight plot, hit enter, you hit graph, and you can see it. We're in the 45s though, all the way up to 45. This goes from 3 to 8, that's fine. Each of these is 1 unit, so that scale is fine. Windows set. So negative 10 to positive 10, if you want to shrink it up to 0 or negative 1, so it makes it a little easier to see, you can. Max is fine up to 10, X scale 1, each line is going to be 1. My minimum here, I'm going to put as a negative 1, and my maximum, I'm going to go ahead and put that one as 50. So that's going to shrink up that window so that I can kind of very well see it. And you're going to see, yet again, we have our one outlier, and it's basically linear. So we're going to go stat, over to calc, and we go down to linreg for this one to create that equation. We'll see how close our actual equation is. It's actually pretty close. 2.8, we have a 2.23, 21.00 versus 25.69. So this is one of those instances where if you had to create an equation and it was free response, you want to make sure that you state how you did it. Did you use the stat and the linreg? Write those directions, those steps down if that's what you did. You can do that as well for park. If you had if you actually graphed it out and used the 2 points and came up with your slope, substituted them in, make sure you put that in as how you did it as well. Show that work. All right, next up. So to estimate ages of trees, forest rangers use a linear model. So we already know this one's linear. So it relates the diameter of the age. Model is useful because the tree diameter is much easier to measure than the tree age, which requires special tools for extracting a representative cross-section of the tree and counting the rings. Use the data in the table below collected for a certain variety of oaks to answer the following questions. We need a linear equation. It's linear, so I'm going to do exactly what I just did with the calculator. We're going to reset. And our diameter is our x. Remember when you're reading a table, left to right, x, y. Top down, x, y. Our age, of course, is going to depend on the diameter. Now, that's a little confusing because the diameter of a tree actually depends on how old it is. However, remember, in this scenario, we're actually trying to find out what the age is. So for us to figure out what the age is, we have to determine that by using the diameter. So that's why it seems a little off. Stat, we're going to do 4. I don't put the point zeros in, but if that was 4.1, you better put 4.1. Oh, and notice I missed that 2.5 at the beginning. So let's make sure we have them all. 2.5, 4.0, I don't care about the 0.0. Once again, if it was a 4.1, I would definitely put that in. Make sure you're typing in exactly as you see it. Making one little mistake is going to mess everything up. Coming over to L2, 15, 24, 32. 15, 24, 32. 56, 49. 76, 90, and 89. So everything's lined up. I won't have it mismatch. I come to stat, over to calc, down to lin reg. I keep hitting enter until it calculates my equation. 6.45 substitutes for A, and negative 0.15 we're going to substitute in for B. Make sure you're rounding correctly as well. So it's going to be y equals 6.45. So y equals 6.45, that goes in for A, or our M, x, which is our slope, minus our y-intercept, 0.15. Now, use the equation to estimate the age of an oak whose diameter is 18. So this is the diameter. That, again, is our x values. The years would be our y. If they gave me the years, I'd substitute for y, solve for x by adding and dividing. Here, I'm going to solve for y by substituting in the 18 for the x. So I have a 6.45 times 18 minus 0.15. Remember, instead of the parentheses, you can do the just straight up multiplication. Hit enter, and I get 115.95. So y equals 115.95. Now, so we're estimating. We are actually going to round up on this one. So y is approximately 116 years old. So if I wrote that in a complete sentence, I would say the oak tree is approximately 116 years old. Make sure that on your free responses on your exam, you're writing in complete sentences and everything when you're given your responses, okay? So make sure you're writing complete sentences. Now, we did round up. This is one of those things with word problems you kind of have to watch. You're going to round up or round down. I didn't round up because it was 0.95. I just round up because it was really close to the 116. And roughly that would work. But if it said at the maximum or something like that, I actually would have rounded down even though it was 0.95. All right, a tennis ball bounces to half its initial height. If the ball is dropped from a height of 24 feet, what is the sum of the first 5 rebound heights? There's a number of ways you can do this. You can just go ahead and use our sum of the geometric series, because that's what this is. We're going to multiply by the original height using our recursive formula. Now, when you do that, you can, again, that formula will be given to you somewhere else in the test if you need to find it to use it. So we're going to do this 2 different ways. I'm going to use the formula to do that. Sum, the total sum, is our first height minus the ratio raised to the number of terms divided by 1 minus r. So if you recall, we did this in like the first video. So the ball bounces to half of the initial height. So remember when we're doing this, we're going half initial height, we're dropping from 24 feet, and we want the first 5 rebounds. So half the initial height would be 1 minus 0.5, because half is 0.5. So we're dropping 50%. So So this gives me a ratio of 0.5. If it increased by 0.5, I'd have a 1.5 as my ratio. A1 is my initial height, A1, and then 5 rebounds is going to be my N. So I'm looking for 5th rebound equals initial height of 24, 1 minus 0.5. Notice again, I still try to keep all decimals, fractions, negatives in parentheses when I substitute them in. Raised to the 5th power, because it's the 5th height, divided by 1 minus 0.5. So I'm going to put that numerator into my calculator. 1 minus, making sure that that 0.5 is in parentheses, raised to the 5th, pulling out of that by the over sign, and hit enter, and I get 23.25. So my numerator is 23.25. Now 1 minus r, again my ratio, is a 0.5. So when I divide by 0.5, I get 46.5. So .5 feet. Now, if I did a recursive, and this is choice A, if I did a recursive for this, I'm saying that my initial height, A0 equals 24, and my new heights are AN minus 1 times our value of 0.5. That's our ratio. We're coming back to half the height. And again, this is for all bounces. We're doing bounces 1 through 5. And since we're doing 1 through 5, we can actually write that as an interval and say 1 to 5. Those are the only intervals we're going to do. So if I make a table chart for N and AN, N being my X, AN being my Y, 0, 24, 1, 2, 3, 4, 5. So let's look at this right here. So I'm going to take my initial height of 24, multiply that by 0.5. My first bounce gets to 12. Multiply by 0.5. Second bounce is a 6. Then it goes to 3. So 12, 6, 3. So 12, 6, and 3. And then 1.5. And one more time, and we get 0.75. This is just a little bit hair off. So now we're going to go ahead and we're going to add these up. Okay? So this is where it just becomes a little bit tricky because you're going to see where there's a mistake over here where students are going to do the same mistake over. So you have to watch this very carefully. If I look at this and I add this up, 12 plus 6 plus 3 plus 1.5 plus 0.75. And I get 23.25. So here's the question. If you look at the entire thing, where's the mistake on the left side? Because the actual truth is 23.25 feet. So if you look at it, and if you caught it while I was working through it, good job. If not, it's okay, because it's a very easy mistake to make. This is my initial height. This is my A0. Okay? It's asking after the first 5 rebounds. What is the sum of the first 5 rebound heights? Not asking for this height. So this is technically A0, which is the way that I wrote it over here because that's the way I read it. I'm wanting to find the first 5 rebound heights. This is not included. If it was included, I'd be up to about the 45. With that being said, that means that we have to change our initial height right here of 24. So again, if you caught that, good job. Our first height, half, the rebound back is a 12. So we're going to put, 12, substitute 12 instead into the equation. So now it's going to be the 12 times 1 minus and we're going to put 0.5 raised to the 5th. So my first rebound height is 12. I'm looking for the rest. And I hit enter and I get 11.625. When I go in and divide by 0.5, I get the 23.25. So if you're just going off of the formula in the beginning, you have to be careful. Look, once A1, not A0. A0 is our initial. That's where it crossed that y-axis. It's where it intersected at 0.24. That first drop down comes back up, and that first rebound height is at 12. So you have to make sure you don't mess that up. All right. Next one up. Okay, here we go. A student eats a set of Pop-Tarts each morning. Each Pop-Tart contains 200 calories. The human body metabolizes 15% of the calories each hour. How long will it take for the student to have used up all the calories? All right, we have 200 calories to get rid of. We're metabolizing 15% each hour. Here we go. The equation is going to be y equals a 1 minus r raised to the x. So I'm trying to figure out basically x. X is going to be my time. R is my rate change, A is my initial amount. So my A and my initial amount is 200. We're always doing 1, and we're going to do 1 minus because we're metabolizing. If we're metabolizing, that means it's sending it out. If I was absorbing, I'd be adding. But because I'm metabolizing, I'm sending it out. 15%, if I divide that by 100, gives me the decimal of 0.15. So that's what I'm going to be subtracting raised to the x. Now, there's a couple of ways you can do this. This becomes 0.85 raised to the x. Now, next semester we're going to learn about logarithms, and this is actually how you would solve this, is by actually doing a logarithm. So 0 equals 200, sorry, my thing will do that, 0.85 to the x. You would solve that for 0 by doing logarithms. We have not touched those yet. So what I'm going to do is I'm going to actually use my calculator. I'm going to come in here. I'm going to put that into y equals. Resetting my calculator, y equals 200, 0.85 raised to the x. And second graph gives me a table of values. I'm looking for when it metabolizes out of the body. So if I keep looking, we've got our first hour, because this was initial. First hour is 170, and you can see that it's definitely decreasing. It's going down, going down, going down. Now it's starting to slow, going down by 3s, going down by 2s, getting down, getting down, getting down. And if you notice, it's starting now to go down by the decimals. And the question is it ever actually going to completely metabolize out of your body? It's really not going to. So you're going to keep those calories in you unless you kind of exercise. So the question of this would actually be never. So what I'm going to do, I'm going to change it a little bit. I'm actually going to say not when you've used up all the calories, because technically you're still going to have a little bit of in. It looks like almost 50 hours later. Let's say when you've got remaining, let's say 100 calories. So I'm going to go back into my plot here, and I'm going to look for where it's at about 100 calories. I'm going to use this here because it just makes it easier for me. Because I can scroll up this way. So I'm looking for 100 calories. I'm at the 40s, 50s, 60s, 70s. Whoop, too far. All right. So if I scroll down and keep scrolling down here, you'll see that between 4 and 5 hours, I've actually dropped from 104 to 88. So at 4 hours, you have not metabolized down to 100 calories. So you can't say that. You're not down to the 100 yet. So I would say in 5 hours, I metabolize. So this would be in 5 hours. The student would have burned 100 calories. Now, let me explain that again. Correct. In 5 hours, they're down to 88. But at 4 hours, they've not reached that 100 calorie mark. So we can't say 4 hours. It's actually about 4 hours and 15 minutes what we're looking at. And those of you going to pre-calc, you actually define that right down to the minute. We also, when we do logarithms, could get that right down to the exact amount. All right, which functions below are even? So you remember that if we end up and up, these are even. Or if we are down, up, or up, down, these are odds. Now, these, again, are even, and they're also based off of the numbers, off the degree. So we're looking at the degree, the numbers of the degree. And this is, of course, your leading degree. So if your leading degree is an even number, then it's an even function. If it's an odd number, it's an odd function. It's that simple. But you got to make sure it's the highest degree. So if I look at this one, 4, yep, that's definitely up and up, and it's even, so that one would be 1. So this one we want even, I'll circle 1. Raised to the 6th power is highest degree, yep, that's true. 3rd degree is odd, and then if it's just an x, like x, that'd be x to the 1st, that would be odd. Now this almost looks odd because it's x and just a 1st power in here, but remember it's absolute value. So this one right here is actually going to end up and up. Because it's a vertical stretch of 2, it ends up and up. So that would mean that I've got to include 1, 2, and 4. So my choice here would be B. Now, if you aren't sure about the graph on that one, because you're a little stressed, you can always type that in. Y equals 2. Come to your math button. You'll come over to number. And right there's abs, absolute value. Put in your x and graph it. And you can actually see that graph, and you'll see that it ends up and up is the end behavior. Okay, here's the doozy of a question. Suppose your aunt started a new dosage of 50 milligrams of allergy medicine, and she takes it every day at the same time. Her body eliminates 40% of the medicine each day. Create a mathematical model for the scenario and determine the amount of medicine in her blood after 5 doses. Explain your reasoning. Okay, so here's the deal with part A. We did these on table charts, on our graphs. We have all of those in here. We did recursive formulas. So here's the deal with this one. It's a little difficult, but if you can get this concept, you're fine. So we have our dosage of medicine. She takes 50 milligrams. Then she's going to take it every day. So she doesn't take it one time. If she took it just the one time, we would just be multiplying by we'd be multiplying 50 and however much it's eliminating and be done, recursive. However, I've got to add back in that extra 50 every single time. So it eliminates 40% each day. The word eliminates, pushing out again. So that's subtracting. If I was adding it, it'd be adding it. If I was putting it into my body and it was building on top of itself, that'd be adding. This eliminates, we're pushing it out. 40% every day. So 40% elimination every single day is represented, again, this is still 1. The number 1 represents 100% of the medicine. So we're putting 100% in, 40% is getting eliminated out. So 40%, again, 40 divided by 100 gives me 0.4. So that's a 0.6. This is what's going into our recursive formula. So our first amount dosage is 50. Okay? That's the initial part we took. Now we're talking about the very next day. So we take it every day at the same time. So AN equals AN minus 1 times 0.6 plus 50. So 0.6 is what we're multiplying the previous amount by and then adding another 50 back in. So basically, on the first day, I'm going to take 50, which was the first amount I took, multiply by 0.6, and then I'm going to add 50 back in every single day. Now, you can also see this written as AN equals, oops. Some people like to put the 0.6 in front. So 0.6 times AN minus 1 plus 50. So you can see it either way, either one of these. Now, of course, we always have our last little part, the third part, for n greater than or equal to 1. We started at 0, so it's equal to 1. If I started at 1, I'd be greater than 1. But this is initial amount. I'm at the doctor, that's it. I'm now talking about every previous day from that. So 5 doses, I'm going to substitute in 5. Would be starting with is what we're looking for the 5th dosage. So we're actually just going to make a table chart for this one. So we have our N, which is our actual medicine that, or the days that we're taking it, and AN is the dosage that's in our body. I know that at 0, when I first take it, I have 50 milligrams. So we're going to come up here. Be just a second to minimize. All right. So I know at starting it's 50. So now what I need is after 5 full day, after 5 doses. So this is after 5 doses, so this would be my first dose. Now this would be technically my 2nd, 3rd, 4th, and 5th. So you can write it this way. If it does confuse you a little bit with the A0 and starting that way, then you can also change this to A1. So let me explain this again. This is talking about 5 doses. That's the key thing here. 5 doses. First dose is 50. Now if you want to represent that as A0, then that's the first dose. Then I need the 2nd, 3rd, 4th, and 5th dose. If it was talking about the days, this would be my initial dose. The next day would be the first, day 1. So this would be the way to represent it. So we don't confuse, we're going to actually start this at dosage 1. Whoops. And so since we're starting at 1, we're only greater than 1. We don't need to find the first one. We already have the first value. So first value, 2, 3, 4, 5. This is the first dose I'm taking. Now every day I'm taking another 50 after it eliminates 40% in my body. So I'm going to take the 50 and I multiply by 0.6 and then I add another 50. So I have the initial amount multiplied by 0.6 because I've eliminated 40%, adding the 50 that I took that day, and I have 80. Now I'm going to multiply it by 0.6 and add 50 to that. That's the first, the second dose, third dose. Now I'm going to multiply by 0.6 and add 50 again, and I get my next dose. So right now I'm at 80 and then 98. So I'm going to put 80, 98, then 108.8. And now we're going to multiply one more time by 0.6 plus 50. So by the 5th dose, I have 115.28. So after 5 doses, using my table chart, that this is a mathematical model, I have shown that after 5 doses, there is 115.28 which one is it? Milligrams of allergy medicine in the body. Now, if I wanted to see where it began to level off or reach this maximum, I could start looking at that table. I could put, I could keep going and keep going and keep going. So let's look at it this way. I could do times and put in parentheses point, well, not really that, but we're going to do the 115.28. Now times 0.6 plus 50, hit enter, and then times 0.6 plus 50. And I can keep going and keep going. You see now that it went up by 4. Now it's only going up by 2, so times 0.6 plus 50. Now you see it's going up by 1-ish, about 1, almost 1.5, times 0.6 plus 50, times 0.6 plus 50, times 0.6 plus 50. And now you can see that it levels off around 124. So if she keeps taking this medicine, then eventually it's going to level off around 124, about 125. I don't think it's ever going to get to 125. So it's going to be just under 125 milligrams left in her body. So this is what doctors have to do. You don't want to immediately give somebody medicine and then boom, they're up to the amount they need. They need to gradually get up to that amount, or else they could have great effects, they could have side effects on taking that medicine. So it's a gradual increase of their medication. It's still taking the same amount, but it's going to end up keeping around 125 milligrams in their body. So let's look at part B. They said it's just not enough. Then they want you to instead, they're saying it's not effective enough. It's more effective when there is a total of 150 milligrams in that bloodstream. And what you're noticing is we're at 124. We're not high enough. So at that point, we decided, well, we need 150 milligrams. We are still eliminating the same amount, everything. We need to know how much she should take every single day. So at this point, I've got everything set up. This is my equation here. Now, I'm trying to figure out exactly what that is going to be. I need to try to figure out what this right here would be. Okay? Sorry, pause for a minute while I get some water. And, all right, we're still good. All right, just making sure everything's good with the camera and everything. All right. Whew. It's a little toasty in my room. All right, here we go. All right, so where are we at? Oh, we need to figure out how much she needs to take if it's 150 milligrams. Okay. So she needs to get to 150 milligrams. So we're going to say 150 equals, we're still doing this, but a n minus 1 is going to represent 150 times 0.6 plus x. What I'm looking for is what we need to take every single day to make this equal to 150. Okay? So when we multiply 150 times 0.6, and I'm going to scoop that over there so we can get this over here. So I've got 150 times 0.6 is going to be 90. So over here we're going to put 150 equals 90 plus x. Solving for x, I subtract 90, and I end up with 60 milligrams equals x. So I would have to write in order to maintain 150 milligrams of allergy medicine in her body, she would need to take 60 milligrams each day. Now you can kind of see that from looking at the numbers that we came up here with. We saw that 50 was really close, it just wasn't close enough. I have some students who try to do trial and error on this, but if you look at it, it says that you have to justify your answer mathematically. So a mathematical model is not the table. You would actually have to do it, mathematically would work with a table. If it said justify algebraically, that's when you would have to do this one right here. Now what some students did is they kind of did a little trial and error. They would say 50, didn't work, 55, didn't get close enough. So then they just kind of went up by 5s and so forth. And then they came up with 60 actually working and showing a table value, showing that it started to level off at around 150 for the 60 milligrams. All right, almost there. All right, let's see. I've got these last problems. I don't have them on the board, but 35, I'm just going to have to write these in. Oops. So number 35, we want to solve the following equation for x. So remember that you just want to do PEMDAS. You want to do PEMDAS backwards. Parentheses, exponents, multiplication, division, addition, subtraction, go backwards. That's kind of the way that I look at it in a way. But I'm solving for x. I need to move everything away from the x onto the other side of that equal sign. Now if you have to, you're still struggling, draw that line right down that middle of that equal sign so that you know you're transferring to the other side of that line. And we have to do inverse operations. The 4 here is being divided into the entire item. This whole item I'm going to split last. So I'm going to get rid of the 4 by multiplying. So I'd have a 4y equals 3 times x plus c. I'm still solving for x. Parentheses is the first thing in PEMDAS. It's the last thing I'm going to do here. I'm going to go ahead and divide. When I have the 3 on the outside, this is known as distribution, which is also multiplication. And I divide by 3. As a result, I have 4y divided by 3 equals x plus c. Don't distribute the 3. Don't do steps you're going to have to undo. You distribute that 3 to that x, that's fine, but you're going to have to take more out at the end. It doesn't make any sense to do that. Don't do more work than what you have to. I'm pushing things away. Don't put stuff with it. Last thing I'm going to do is I'm going to subtract that z. These are not like terms. They cannot be combined whatsoever. So it's simply 4y divided by 3 minus z is equal to my x. And that's your final answer. Now again, you're going to have some students, you may try to go ahead and distribute that 3, and you're trying to look for something equivalent. If you distribute that, you get a 3x plus 3z divided by 4. Multiplying your 4, you have a 4y equals 3x plus 3z. At this point, if I'm still solving for x, I'd have to subtract the 3z. 4y minus 3z equals 3x. Dividing by 3, 4y minus 3z divided by 3 equals x. At that point, you would distribute the 3 into both terms. 4/3 y minus 3 divided by 3 is 1, so it's a 1z. You see that you get the exact same answer, but why do all this work when you can just do this? Don't distribute if you're pushing stuff away. All right, number 36. On 36, I need to solve for y2. This is our slope formula. So I cannot separate these. These are known as one item. When they're combined by addition and subtraction, it's one item. I can't separate that when we're dealing with this division. So I have to think of a parentheses around each of these. So the first thing to do is I'm going to transfer this entire parentheses to the other side. I'm multiplying both sides by x2 minus x1. If I multiplied it up here, x2 minus x1, you would see that they just eliminate. This divided by this is equal to 1. So I don't do that. I just cross it out and move it. I just perform the inverse operation. So I end up with m times x2 minus x1 equals y2 minus y1. Now at this point I'm solving for y2. So I'm just going to go ahead and I'm going to erase those parentheses because now I've got to get rid of y1. So to get rid of it, I have to add it. None of this can be combined. Even if this was an x1, I could not put the x1 here because they're not like terms and this is in the parentheses. And they're not the like terms because this is in the parentheses. Plus the y1 equals y2. That's your final answer. Now if you wanted to distribute that m all the way across, you would have an mx2 minus mx1 plus y1 equal to y2. So you could distribute that m all the way across. All right, Carmen is working through a math problem to isolate a variable. Follow through his steps to explain the reasoning behind each step and correct any mistakes she may have made. All right, so I'm going to first write all the steps down since, again, I don't have this. So y equals 2 times x minus 5 plus 6. So the steps, we have step 1 is y equals 2x minus 10 plus 6. Step 2, y equals 2x minus 4. And step 3, 4y equals 2x. Step 4, x equals 2y. All right. So that's the step, and it's the reasoning or correction. So if it's correct, you're going to give the reasoning. That's it, justification. If it's not correct, you're going to fix it. Now here's the deal that I always suggest to my students. If you're trying to find an error analysis, work the problem out the way you would, and then compare the steps. So over here, I'm going to write out y equals 2x minus 10, or I'm sorry, I'm going to start from the top part. Y equals 2x minus 5 plus 6. So the first thing that I'm going to do is I'm going to distribute that 2. And I get y equals 2x minus 5 plus 6. My second step is combine like terms. Y equals 2x minus 4. Solving for x, my next step is to add the 4 over. And it becomes a y plus 4. And my last step is to divide by 2. So that I get x equals y plus 4 divided by 2. Or if you distribute that 2 into both terms separately, it's a 1/2 y, or y divided by 2, plus 4 divided by 2 is 2. One of these would be the final answer. You can clearly see it's not correct. So there is a mistake somewhere. So the first thing that I did, I distributed, and I got 2x minus 10 plus 6. You see that's exactly what they have. So the first reasoning is distribute the 2. Now, I ended up combining like terms to get 2x minus 4. It's exactly what they have. So combine like terms. Now, they also add, so that they're solving for x, they add the 4 to both sides. They do inverse operations. So we complete inverse operations, but they combine like terms incorrectly. So this is where the mistake is. So I could cross that out, and I could say add 4 to both sides. Which is inverse operations. I see they have their mistake, so I'm actually going to kind of take this and scoot this down a little bit so I can have some room. And I'm going to bring over the part where they were supposed to have done. So I'm going to over here say add 4 to both sides. Y plus 4 equals 2x. Now my last step is to isolate x by, again, dividing 2. So this is a huge common mistake. Students just go ahead and combine those together. Not like terms, you can't do it. So it's simply y plus 4. Now I do exactly what I did over here, and I just divide it out to 2. And my final answer would be y plus 4 divided by 2 equals x. that would be my final answer. Remember that you're doing inverse operations. If you kind of struggle, honestly, look at your calculator. The addition is above the subtraction sign, and they're above each other, and the multiplication and division are above each other. So those are your inverse operations. And that's what we're talking about is inverse operations, opposite operations. Remember, side by side would be multiplying. Think about bunnies. When they're side by side, they multiply. And then you can divide them out to get rid of them. So that will be the entire Algebra 2 Semester 1 final review. I know the video quality is not the best in the world, but at least it gets you through it so that you can review at your own pace, stop, rewind, do whatever it is you need to do. Good luck. Please have recorded.